All right, so this is it's not Math This is just Math331, problem solving, lecture 25, I think, something like that. So we've learned how to do the 2x2 cube. If you haven't demonstrated it today, I will give you another opportunity to do so later. I really want you to have the skill, and part of it is to learn how to reduce things to simpler problems, solve them, and then build up to the more complicated ones. We have seen this several times during the semester. Frequently, a problem is given to you at the higher level. And the people who propose the problem do not emphasize the fact that you should start at a small level, build intuition, and then attack the problem that they propose. We are coming up to Putnam season, where if you get 1 out of 120 points, that is a good score. This is a hellish exam. On problems like that, try to do small, simple cases and build intuition. So we've talked about solving a 2x2. And again, part of it is trying to learn things in such a way as to minimize the number of moves you need. May I borrow your cube? So, perfectly solved cube. If we mix it up a little bit, if we are able to solve red as we go, so here's red, white, where's another red, white, here's a red, white over here. I want to try to walk it up. And if I spend some time like this carefully walking it up, and then here's red, green, I can walk that up. And then here's the last one over here. I need to do the goodbye friend, hello friend move. So goodbye friend, walk up, hello friend. That makes my life much easier. I now have red solved. But if I didn't see that, if I instead had something like this, let's actually make it a little bit worse even. So now I have it like this, where I've got 3 reds on top, and this one is a yellow. I could actually do the up, left, down, right move to make this red on the bottom. So I could go up, left, down, right, up, left, down, right. I don't care if I'm screwing up the top because I haven't really gone into the top yet. And now I look at the bottom and I see I've got all reds. These two are correct, red into white, but these two are wrong. So I can use my last move to switch these. I can do the up, left, down, spin, up, right, down, and then sesame spin, up, left, down. And that will fix the reds. It screws up the top, but the top was already screwed up, so it doesn't really matter. We then have the up, left, down, right move, so I can just keep doing up, left, down, right, up, left, down, right, up, left, down, right, up, left, down, right. Keep moving, and just keep going around. Now you notice this is very slow. There's a lot of steps this is taking. This is not a great way to solve the cube. If you want speed, this is not the way to get speed. And now we've got 2 sides here that are right and the other 2 are wrong on the bottom. So I want to switch it so I have exactly one that's right. So I want this one and I want to switch the opposite corner. So it'll be up, left, down, double spin to launch because I want to switch with this one. Up, right, down, sesame spin. This is the one that's different. Up, left, down. These 2 are now correct, so the 2 in the back are now wrong. So I move those 2 here. Now I want to switch these. Up, right, down, spin, up, left, down, sesame spin, up, right, down. Then we leave the rest as an exercise to the reader. Okay? So the idea is, how many moves do you really need to learn? We had this up, left, down, right move, which we could actually use to help solve the first level. And then we had the complicated up, left, down, up, right, down, up, left, down, up, right, down, up, left, down, up, right, down, which we used to finish the bottom. We can also use that to solve the top. So if you don't want to solve the top, you could actually solve the top by using some of those more complicated moves. It makes your life even worse, it takes even longer, but the number of moves you need to learn is even smaller. When Kayla was first starting to learn how to solve the cube, I will not say I was frustrated. I was trying to remember, well, she is 5 years old. She was having trouble solving the reds. So what do you do when you have somebody who's having trouble learning step 1?
Do it for them.
So one thing is, okay, so if I do it for them, then what do they learn?
How to do all the other ones?
Yeah, so actually, what we did is, I said, I will get you the red set up. Let's hold off on that for now. Let's work on step 2, so that you have something that you can be proud of, and you can go from that. So again, part of the reason is I really want to talk to you about how do you present material. Which do you think is easier, step 1 getting all the reds, or step 2 up, left, down, right, up, left, down, right?
Step 2.
Step 2. Now, there was a challenge for Kayla that she actually didn't know her left from her right. And this is actually when in her life she finally learned left hand from right hand because it mattered for solving the Rubik's Cube. But it was a much easier step to learn that. And then building on that success, we then went back and did step 1 and then eventually got on to step 3. So now let's look at a 3x3 cube. So I don't want to spend too much fast time doing this. There are lectures online. I'm going to still solve red. So here's, on this cube, it's pink. So here's pink into blue. So I line that with its center. So this is one of the differences with a 3x3 cube from a 2x2. We actually have centers now. So now I look for, here's another one. Here is pink green. So okay, so here's my green center over here. So a lot of it's just playing with it. So if I move it down over here, I spin it around here, and I can just walk that up. So I'm basically trying to do a plus side and then leave the corners. Why do you think I'm trying to leave the corners? Why do you think I'm doing the plus side first and not the corners?
The corners reduce to the 2x2.
Yeah, the corners reduce to the 2x2. So I now look over here. Here's a red-white. So I line this up with the white side, and then I spin that up. Notice I've got a lot more reds up here. These are wrong. I'll have to deal with that later. And now here's the last. Here's red-yellow. So I now spin that up. And so, it looks good, but unfortunately, every single corner I think is wrong. And that's fine. I know how to drop a corner down. And now here's the blue-white corner. So here's blue. So blue-white needs to come up here. So what I'll do is I'll just move this out, bring this down, move this over, and move this back up. And so if you just play with it for a little bit, now here's red, green, here's red, green, yellow, here's green, here's yellow, so I want to move it to here. There's a couple of ways you can do it. If I just spin this down here, move this over, and move this back, I'm fixing the corners one at a time. Here's red, white, green, so here's my white, here's my green, I want it to come up here. Yeah, I'd love to put it up here, so one thing I could do is I could push these two out of the way, pull this up and do that. The goodbye friend, hello friend. There's lots of ways you can do it. The last one over here, I want to move this up. I could do goodbye friend, hello friend. Lots of ways you can do it. I now have the first side solved, and I've got it coming up like this. So now, is the next thing, is this the next level something we know from the 2x2, or is it something new? What do you think? Do we need a new move? Yeah, we've solved the first level. The 2x2 doesn't have a middle level. So when you're trying to think of how many new moves do we have, if you can do the first side, you can basically do that without learning a new move. I want to show you need to learn only 2 moves if you can do the first side to do a 3x3. So once you have a 2x2, it's not that bad to go up to a 3x3. This is why I teach you this way. And if you want to go up to a 4x4, 5x5, 6x6, there's only a few moves you need to learn. By the time you get to either the 6 or the 7, you've learned all the moves. And essentially what just happens is on the 4x4, you have to learn an edge move, and you have to learn a center move. And the center move isn't too bad. And then you have to learn parity moves. The even cubes are painful except for the 2x2. All right, so the move we need to learn now is a drop-down move. So this piece is white-green. Here's the white corner, here's the green corner. This piece wants to be here. I'd love to put it here, but then that screws up a lot of other things. So I need a move that will drop this down. And so it's just a sequence of moves you need to learn. So to drop this down here, I line it up so that the side here matches the center here, and I want to drop it down this way. I don't want to do it this way, I want to drop it down this way. So the move is I go opposite, up, back, down, continue, up, back, down, and it's dropped down. So it's just a new move you have to learn. Notice over here that I've got a white-blue piece over here. It wants to be here, but it's in the wrong orientation. So you just reach in and, no. So you don't reach in and twist. What would I do? This piece is in the wrong orientation.
To pull it up and then you
So how do I pull it out?
You put in a different piece.
Yeah, you drop anything down. So I'll wait for later for that. But eventually I'm going to just drop a piece down there to free it up. So here's blue-yellow. I want to drop blue-yellow here. So I go opposite, up, back, down, and then I continue walking. And now I spin up this way. And if you look, I've got the pink here. I'm going to want to move the pink back. So that tells me I want to move it this way so the pinks can align. Again, it's just a move you need to learn. Now the only one that's left is this piece here. So what I have to do is I just drop any piece down. I don't care. Well, if I look at this, of the pieces in the top, I've got to choose one of these four to drop. Which one should I drop? You have four choices. One is good, three is bad.
Could you repeat that?
Sure, I've got four pieces that I could drop down. One of the choices is good, three of the choices are bad. That should be a real hint. Which piece should I drop down?
Blue piece?
Yeah, because this is the piece that doesn't have an orange facing on the bottom. I want to get oranges facing on the bottom, so since this piece I know is not right, let me drop that one down. These pieces are actually already good, they've got oranges on the bottom. So I'm going to drop this one. So I need to drop that one here. Should I have it on this side or on this side? It doesn't matter, right? Because it's wrong, it's not supposed to go there. I can drop it either way. So I'll drop it down this way, so I'll go, I just do my move, and now my new piece is up here, and now I want to drop this down. So I do my drop move. Okay. Now I actually lucked out that all four of my oranges in the middles are correct. How do I solve these two over here?
The 2x2?
Yeah, the up, left, down, right. So I just go up, left, down, right, up, left, down, right, up, left, down, right, up, left, down, right, move up, left, down, right, up, left, down, right. So what I'm going to do now is I'm going to just screw up okay. So I just screwed up two of the oranges on the bottom, just so I could teach you the move. What would be your first thought to try to fix these? What might you try? I've never tried it. I have no idea if it'll work. I'm happy to try it. How did we fix these corner pieces?
You can do the 2x2 move.
You could try up, left, down, right. I could try up, left, down, right, up, left, down, right, up, left, down, right, up, left, down, right, up, left, down, right. And I've returned to where I was. This is the nice thing about a cube. There's a group structure on it. So if you know anything about groups or abstract algebra, if you keep doing the same move, you will eventually return to where you started. Unfortunately, that move doesn't work. I returned to where I started and I never have it flipped. I was pretty sure it wouldn't work. So why was I pretty sure it wouldn't work?
Up, left, down, right works if you have it in like a recording position, right?
There's a higher level reason why I was sure it wouldn't work.
The up isn't the same.
No.
Oh.
Nope. This is a good way to cheat in life. And again, this is one of the reasons why I'm telling you this. If you are taking a Putnam exam or a math competition, you have a huge advantage. The problem is solvable. You know it's solvable. So one of my professors, Peter Jones at Yale, had a lot of wonderful pieces of advice. You know, he said that there are really two things you can do in math proofs. You can multiply by 1, and you can add 0. He said, well, the log of 1 is 0, so there's really only one thing you can do in mathematics. So if you look at things, you know, one of the things we can do algebraically is we can add a 0 or we can multiply by 1 and then find good ways to manipulate it. The other thing, and this works the better you are, if you are, let's say, a prominent star mathematician with years of experience, should you be aware of certain results? Yes. If you're not aware of them, is this unfair to the poor students who are taking your class that they have a professor who is not familiar with the literature? Yes. So by the time you're old, by the time you're established, you should be aware of things. If you haven't heard of a result that's really elementary, that should be known, what can you guess?
It's not
It's probably not true. So given the fact that I've never seen that move, and that the people who taught me never showed me that move, and they showed me a more complicated move to fix, is it possible they ignored something simple? Absolutely. Absolutely possible that they ignored something simple. But the more likely explanation is they never taught it to me because it's not true. How many of you actually do know what the definition of a group is? So a group is something that has 4 properties. When I was taking my general exam at Princeton to get my master's, I was given a question: is the following an equivalent definition of a group? And it did not match any of the definitions I had seen in the 5 or 6 different books I looked at to prepare for my general exam. So I immediately said it's not a group. And they said, good, now prove it. So then I was just either show that it's contradictory or come up with a counterexample. Something that satisfies all those properties but is not a group. And so I very quickly came up with a counterexample by exploring like 2 or 3 element possibilities. So if you have some intuition, you can take theorems, and if you remove a condition, is the theorem still true? Well, if you've taught a lot of classes, you should be aware of the theorems, and you should be aware of what conditions you need. If you've never heard of the mean value theorem with non-differentiable functions, almost surely differentiable is central to the proof. Sometimes these conditions are just to make proofs easier, like the fundamental theorem of calculus. You do not need to assume your function is differentiable, but it helps. All right. Unfortunately, this cube is going to be in great shape, but all right. I'm going to fix these corners now, these middles, with a new move. It's the second move you need to learn. So we talked about the drop-down move first. So here, I put orange on the top, I spin this right, move this twice, once, twice, then I move this twice. Does it matter which way I move it twice? No. Then I move it once more over here, so it's now gone all the way around. And this is why I do the corners first, because when I'm moving it up, I see I get orange into orange. Now I move the other one into position. Notice how we've screwed up the bottom? We're used to stuff like that. So before I went to the right, what should I do now? Left. Before I did 2 and then 1, what should I do now?
1 and 2.
1, spin this twice, and now do twice more. Once, twice. And that's your new move. Bottom is now fixed, and now you have all the stuff here. All right. This cube has the centers already solved, the corners already solved. Will you just agree with me you would solve the corners using the up, left, down, right? I'm sorry, the up, left, down, up, right, down, up, left, down, up, right, down, up, left, down, up, right, down move. Exactly as before in the 2 by 2. So now the only thing I need to teach you is how to solve the middles. Any thoughts on how I should solve the middles? By the way, I'm not allowing you to learn any new moves. Can't learn any new moves. You can only use existing moves you have. What should you try to solve the middles? What can we try?
Up, left, down, right.
So we could try up, left, down, but we've seen that up, left, down, right doesn't really fix things.
The one that you just showed us to move the middle piece.
To move the middle piece? Well, that only changes these to put the orange on the bottom. I could do that to flip the blue to be over there.
Okay.
So we solved the corners.
Whatever you did for the side middles.
To drop things down. Well, the way I got the side middles was I was dropping pieces down. So I can't use that here. How did I get the corners correctly? I didn't do it because my cube was fine, but what move do I use to get the corners? The up, left, down, up, right, down, up, left, down. What should I try for these? Let's try the same thing, right? So over here, here's blue, here's white, and here's yellow. So 3 things are wrong, 1 thing is correct. So if I switch blue and white, then I'll have to switch white and yellow afterwards. So I'm going to go up, left, down. I want to switch that with this. So I now move this to launch, up, right, down, and now sesame spin, up, left, down. So now notice blue and green are correct, and the 2 opposites are wrong. So now I want to switch these. So the only difference is rather than launching from the bottom right, I'm now launching from the middle. Now I go up, right, down, I wanted to switch with the one behind it, so spin twice, up, left, down, sesame spin, up, right, down. And that's the 3x3. So there really isn't that much more to do with the 3x3 than with the 2x2. You've got to learn a drop-down move. You've got to learn a different flip for the bottom. So if you can learn the 2x2, you're not that far from learning the 3x3. And so if you want to learn the 3x3, I've got plenty in my office. I was talking a little bit before class. This is a 6x6 cube. The 6x6 cube actually has all the other smaller cubes built into it. So what's the easiest cube to show is built into this? You can be really generic and stupid.
The 1x1.
The 1x1, okay? The 1x1 with just, it's okay. The 1x1 is not interesting. What's the first interesting cube? The 2x2. And so if I just move it in groups of 3, it's a 2x2 cube. So I can actually use this as a giant 2x2 cube. The next one is a 3x3. Can I make it a 3x3? Sure. If I move it in groups of 2 now, you can start to see, there's my... But there's actually 2 different ways of getting a 3x3. One way was to do that in groups of 2. The other is these 4 pieces always move together, these 4 together, these 4 together, and these 4 together. So if you do it like that, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll draw it on the board. So boom, 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 boom. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I just moved these blocks of 4 always together. So I always move the middle 4 rows or the middle 4 columns. And as long as I just move like that, and I can of course also spin just the top or just the bottom or just the sides, that will give me another 3x3. So in fact, one of the ways you solve the bigger cubes is you solve the centers first, then you get the sides or the edges to be correct, and then you treat it as a giant 3x3, where the center is solved and now you move things in blocks like that. The difficulty is if your cube is even, there could be some flips, but it's essentially what you do for the higher ones. Can you treat this as a 4x4? Sure. Just move these 2 always together and move these 2 always together. Just imagine that they're glued together. And then you've got a giant 4x4. And for a 5x5, I think if you just move the middle 2 together, that's a 5x5. So if you buy just one cube, it's the same as all the others. In terms of actually working with it, it's going to be a lot harder. And it's a lot harder to remember, I've got to keep these 2 together, and you're likely to make a mistake. But it's worth seeing. All right, so just a few other general thoughts. It's worth getting a sense of the complexity of the cubes. Do you have the pentagon cube on you that I lent you? Excellent. All right.
I don't.
You don't? All right. So cube cost. So if I give you, n by n by n number of pieces. So if I give you a 2 by 2 by 2 cube, how many pieces?
8.
8. If I give you a 3 by 3, how many?
27.
Not 27.
26.
26. Why 26?
The middle is not a piece.
Yeah, the middle is not accessible. How should I write the number 26? So some string theorists would say it's 3 times 8 plus 2, and they were like Clifford algebras, so 27 minus 1. There's a better way than writing it as 27 minus 1, though.
27 minus 3 minus 2.
No.
27, 3 cubed.
3,
minus 1
yes. So if we're going to write that as 3 cubed minus what?
1 cube.
Minus 1 cubed. How should I write 8?
2 cubed minus 0 cubed.
2 cubed minus 0 cubed. And so if I give you a 4 by 4,
4 cubed minus 2.
be careful how you say that out loud. Okay? If you just mispronounce that, it sounds like profanity. All right. So, and in general, if I give you an n, it's n cubed minus n minus 2 cubed. So what you can do is you can look at what is the additional cost as you go up. You know, the n cubed minus the n minus 1 cubed. So this would be n cubed minus, or do we want to go up maybe to the n plus 1? Maybe we'll have the n cubed here and have the n plus 1 over here. So it would be n plus 1 cubed minus n minus 1 cubed. Then we have to subtract off n cubed and add in n minus 2 cubed. So just quickly looking at this, how do you think this grows? What do you think the growth rate's going to be?
O of n cubed?
So O of n cubed is correct, but can you do better? I mean, we could of course expand everything out, but just when you look at this, do you think this is growing cubically? Why not?
Because you have all the coefficients are 1.
All the coefficients are 1.
And you have...
Or negative 1.
Yeah. And you have 2 positive n cubes and 2 negative
Yeah.
n cubes.
So the n cubed here is going to cancel the n cubed here. The n cubed here is going to cancel the n cubed here. Or I could even subtract directly. And if I look at just this level, I'll have a plus 3n squared and then a minus 3n squared. So that's going to become, I think, a 6n squared. And then the next piece will be so then I would have we're going to be very careful. Right. Then the next piece over here, I'm going to have 2 minus n, so it's going to cancel it out perfectly. So I won't have the n term. And then I'll have a plus 1 and a minus negative 1 cubed, so I'll have a plus 2 from that. Over here, what am I going to have? The n cubed is going to cancel the n cubed over here. And now when I expand this out, I'll have a minus 6n squared. Oh, there's is it a minus 6n squared?
Yeah, I think so.
And then what comes next? Then it'll be a plus 4n.
Wouldn't it be...
Plus, 12n. Right, and then a minus 8. So it looks like it becomes 12n minus 6. So if we check, this is 8, this is 27, this is 64 minus 8. 64 is 56. So going from 8 to 27 is 19. So when n is 2, 24 minus 6 is 18. Oh wait, this is 26, not 27. Which is 18. Good. And then over here, this is 30, I think. And so if we take n equals 3, 36 minus 6 is 30. So this seems to be correct. Again, the better way, of course, is to just carefully expand things out. But this should be a little surprising. Not only do the main terms cancel, but the secondary terms cancel as well. There's a little bit of a miracle here. That if you're looking at the growth in cost, the growth in cost is actually linear. And so you're trying to get a sense of how expensive is it to make a cube, or how long will it take you to solve it. You really want to get a sense of what the right way to look at this is. I am going to risk mentioning a result from calculus. Anybody remember Simpson's rule, or at least can fake it, so I feel that there's some good education happening in high school? Anybody have a good straight face? Oh yeah, Simpson's rule. I remember we talked. Do anybody remember like the trapezoidal rules to try to estimate the areas under curves and trying to do a good job? There's a little bit of a miracle in Simpson's rule in terms of how well it does. It actually does one order better than you might expect because of how things cancel. And this is just something I wanted to get on your radar screen, that sometimes problems are not as bad as you might expect. That there is a cancellation that occurs and the complexity is not as bad. When you're writing code, you really want to know how long it's going to take to run, and if I'm going to scale up, how bad is it going to be? In Mathematica, if you're storing things in arrays, it's expensive. The longer the array is, the more of a cost it is to work with the array. It doesn't seem to be linear. So in terms of how things scale up, that's going to be a real issue. So over here, what I wanted you to see is, to get some idea of how much longer it will take, is you want to get a sense of how many moves do you need to do. So I haven't really shown you the additional moves you need to do on this. But it would be an interesting question, if you know how to do the cubes, how much harder do you think it's going to be? How much more time do you think it's going to do if you can do a 7x7 to do an 8x8, a 9x9, a 10x10? And can you estimate roughly? A lot of it is, oh God, I just have to do this move 100 times. And just slowly fix these things. There's a lot of really great web animations where they will take a 1,000x1,000 cube and the computer will solve it. Now, we are not going to build a 1,000x1,000 cube, sadly. But you can build it, and you can just have the computer manipulate it and use the algorithms. And you can see all of a sudden the structure emerge. And to me, that's one of the other things that's fascinating about this, is that you could be playing with this for a while, and it looks like you're making very minimal progress, and then all of a sudden, boom, it just really starts to solve. And there's a lot of problems like that in mathematics where there's a certain critical threshold that when you reach this, one of the best examples is the birth of the giant component. And we'll probably end the day with that. So imagine you have a bunch of dots in the universe, and you want to connect them. And at every moment in time, you look at all pairs of unconnected vertices, and you randomly choose one of them to connect. Okay? And then you can ask what happens as time evolves. And so maybe I first connect these, then this, 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 then this. So right now, nothing is really that big, but then all of a sudden, maybe I end up getting this connection and then that connection in 2 moves. And the largest component size grew greatly. So there's a lot of wonderful papers called The Birth of the Giant Component, where at a certain critical number of edges being added, all of a sudden, the size of the largest component changes greatly. I think you can also do this by having probabilities that each edge is chosen, and then seeing what structure emerges as a function of the probability of connecting edges. And this is extremely valuable in network theory. How might this be relevant to your life? Something like this.
Internet connection?
Yeah, internet connections, social networks, in terms of who do you know? So much of life is, do you have connections? Can you pick up the phone and call in a favor? This is one of the reasons why you come to Williams. This is one of the reasons why you try to impress your professors as well as the upperclassmen who will go off into the real world before you. Right? I have told the story to some people, not to others. You would think this would be filed under the blatantly obvious things of thou shalt not do. But a couple of years ago, a colleague of mine set up an interview for a student of hers at a big firm in New York City. And the company said, we're really excited to meet you. We'll see you at 8:30 a.m. at our headquarters. And the student wrote back, oh, I'm not a morning person. Let's meet in the afternoon. So, turns out the company was not a her type of person either, and lost the interview, did not get the job, and my friend can no longer recommend anyone to that company. So, again, this should be blatantly obvious that you don't do. If you want, you can say, I'm actually donating a kidney to save a life. at 8 o'clock that day. I don't think I'll be out from anesthesia until later in the day. But if necessary, I can see if we can do the surgery in your lobby. If there is an absolute must reason why you can't make the interview, give it to them. Don't just say you're not a morning person. Okay? But this network of connections, you don't know who will become important in your life. Years ago, I was leading a trip to Boston as part of the neighborhoods, and there was somebody wearing a Williams shirt walking the streets. And this is kind of a little creepy. Somebody took a picture, posted it on Facebook, and within a minute, the student was identified. You have a very powerful network. If you are having trouble finding jobs, if you are not sure what you want to do with your life, talk to me, talk to other people, and we will spread your questions throughout the network. This is why you want something that is as connected as possible. This is why you want to go to a college that has these connections. All right, this is a good place to stop.